In the last lecture, we had tried to derive an expression for the self inductance of a distributed winding on the stator of a salient rotor cylindrical stator machine. In order to do that, what we had done was first look at the MMF distribution generated by exciting the stator winding as you travel around the circumference of the air gap. We plotted that distribution and we found out the fundamental component of that distribution, and then that was resolved into two directions along the axis of the pole face and along an axis 90 degrees to that of the pole face, and then we tried to find out the net flux linkage in the stator winding. In order to do that, again we considered an elementary coil in the stator winding, found out the flux linkage of the elementary coil, and then using that expression we perform another integration over the span of the winding, and when we did that, what we have is an expression here. This expression was the flux linkage of the elementary coil, and then in order to get the flux linkage of the entire winding, we integrate over the span of the winding being denoted by beta, and we were integrating that and you got psi s equal to this much. Now let us try to simplify this relation and proceed further. The integration that we have done, when you substitute the limits, the first term, that is sine of gamma minus theta r going from pi minus beta by 2 to pi plus beta by 2, can then be written as sine of pi minus theta r plus beta by 2 minus sine of pi minus theta r minus beta by 2. So this is of the sine a plus b minus sine a minus b form. So this is 2 times cos of pi minus theta r into sine beta by 2, which is nothing but minus 2 cos theta r sine beta by 2. The second part of the expression can then be written as cos of gamma minus theta r going from pi minus beta by 2 to pi plus beta by 2, which is cos of pi minus theta r plus beta by 2 minus cos of pi minus theta r minus beta by 2. This is of the cos a plus b minus cos a minus b form. So that is nothing but minus 2 sine pi minus theta r sine beta by 2, and therefore the expression for the flux linkage can then be written as psi s equals 2, and we will take this 2 also outside, which means it is 4 f hat z mu naught r l into cos square theta r by L G D plus sin square theta r by L G Q multiplied by sin beta by 2. Because the sin beta by 2 expression is common to both, we can take it out. Now this can further be simplified as 4 f hat z mu naught r l into 1 plus cos 2 theta r by 2 times L G D plus 1 minus cos 2 theta r by 2 times LGQ into sin beta by 2, and we rewrite this as 4 f hat z mu naught r l 1 by 2 LGD plus 1 by 2 LGQ plus 1 by 2 LGD minus 1 by 2 LGQ into cos 2 theta r into sin beta by 2. Now let us define two inductance terms, one which we will call as LD. There must be a term IS here, that is missing. This is IS, there is also a term IS that was missing there. Okay. Now we will define two inductance terms, one of which we will call as LD, which is 4 times f hat z mu naught r l by LGD, and f hat being 8 times IS is there inside that, so that is right, IS would not come here explicitly, IS is already embedded in f hat. So let us first expand this term. F hat is nothing but 8 times z is by 2 pi sin beta by 2. This expression we get from our earlier derivation of as is seen here, where we try to get the amplitude of the fundamental component of the MMF distribution, that was our f hat, and therefore we substitute that here, and using this then what we have is psi s is nothing but 32 times z square sin square beta by 2 mu naught r into L divided by 2 pi into 1 by 2 LGD plus 1 by 2 LGQ cos 2 theta r multiplied by IS. Now we will define an inductance term LD as 32 z square sin square beta by 2 into mu naught RL by 2 pi into LGD, and another inductance term LQ as 32 z square sin square beta by 2 mu naught RL by 2 pi into LGQ. This inductance LD is representative of the assumed cylindrical rotor structure with an air gap of LGD, which is a smaller air gap, and another inductance LQ which is representative of a cylindrical rotor structure which has an air gap of LGQ, which is a larger air gap, and the larger air gap is the one that is present along the quadrature axis 90 degrees to that of the pole face. So we will call this as quadrature axis inductance, and we will call this, since it represents the inductance at the smaller air gap and therefore the inductance along the axis of the pole face, we will call that as the direct axis inductance. With this, then the expression for psi s can then be rewritten as psi s is equal to L d by 2 plus L q by 2 plus L d by 2 minus L q by 2 into cos 2 theta r multiplied by I s, and therefore the ratio of psi s to I s, which is nothing but the self inductance of the stator, is then given by this term. Therefore, we can write L s is L d plus L q by 2 plus L d minus L q by 2 into cos of 2 theta r. Note that the inductance in the inductance expression we have derived like this. What we are essentially determining is the flux linkage, and in determining the flux linkage we are assuming that the MMF generated by the stator produces flux which crosses the air gap and goes into the rotor, and therefore all of this flux would link in some manner coils that might be on the rotor, and therefore this flux linkage and hence the inductance that we have derived essentially represents the magnetizing inductance of the stator winding. In order to determine the total self inductance, therefore, one has to add the leakage inductance component LL and leakage inductance, which by definition closes itself in the air gap, which might be in the air gap between the stator and the rotor, or it might also be due to flux linkage which is there in the end windings. So, all those effects together add up and is lumped into one leakage inductance term, which we add as LL. So, the total self inductance then is this leakage inductance component plus the magnetizing inductance term. Now, note again that the form of the inductance then has one term which is constant, which does not change, and another term which varies as cos of 2 times theta r, which means that over an angle 0 to 360 degrees, if we now plot this inductance with respect to theta r, let us say that this is 180 degrees and that is 360 degrees and 0 degrees. This curve would then look like this cos 2 theta r variation happens over and above a DC value, which is leakage inductance plus this LD plus LQ by 2. So, let us denote that by this average line. Now, over and above this you now have LD minus LQ by 2 into cos 2 theta r, and therefore at an angle theta equal to 0 this inductance is really maximum. And then at an angle theta equal to 180 degrees you find that this becomes cos of 360 degrees, and therefore this completes one cycle of variation in a span of 360 degrees. So, if we start here and then it goes up to here. So, and then in the next 180 degrees it completes one more cycle. So, you have 2 cycles of variation within 0 to 360 degrees of the mechanical rotor angle. If we neglect the leakage inductance, if we are plotting only the magnetizing inductance part, then this level would denote LD this would denote LQ, then the mean is given by LD plus LQ by 2, and this amplitude is then given by LD minus LQ divided by 2. So, this would then be the form of the expression. Now, if we look back at what was the plot obtained through finite element study for a particular winding, we saw again a similar distribution from 0 to 360 degrees, 0 to 360 degrees. You see that there are 2 cycles of variation, therefore, there must be a cos 2 theta term and a mean term which you have, and the expression is as what we have derived. Therefore, whether the winding is going to be concentrated or distributed, the form of the expression remains the same. We had earlier looked at a single coil on the stator and a salient pole rotor. As it rotates, what will be the nature of inductance variation? That was the plot that we saw earlier. Now, we find that the distributed winding also behaves in the same way. In fact, if we now look at those two expressions, if we make an equivalent number of turns by looking at these expressions, then one can arrive at an equivalent number of turns between which the distributed winding must have in order to be considered as a concentrated winding. So, the nature of the expression still remains the same. Now, AC machines do not just have a single winding on the stator, they have many windings on the stator. Normally, a 3-phase AC machine has 3 windings on the stator consisting of R, Y and B phases. Therefore, we have now looked at the self inductance of the rotor, we have looked at self inductance of the stator. Now, we need to also see what will happen if you have one more winding on the stator, which will then mean there could be a mutual inductance effect between these 2 windings. So, how does the expression for mutual inductance look like? Now, let us understand how the machine geometry looks like before we get into the mutual inductance part of it. So, let us now see how the machine is going to look like. Let us see a picture. Now, here you have an image which we have seen previously in animation. Now, it is just a snapshot of that animation. In this case, we have a 4-pole stator winding, and what is shown is just one pole pair portion of it. So, we see here that the coil enters here, one side of the first coil, so to say, and then the coil closes with the other coil side. There may be many more turns in a coil which is multi-turn coil, but here we are only considering a single turn to simplify the view, and therefore, it goes around, comes here, and then around the circumference on the other side it goes, that completes one turn, and then the coil has a second turn which goes around here and then comes out. Now, this would be the way the winding would be represented or would look like in the actual machine. Now, in this case what happens is that you would have within this region, within this circumference of the stator, you would have a large MMF, and the MMF decreases as you go outside, the axis of the MMF would then be situated there, and from the center if you draw a line to this point and you take it out, so that would be the direction of the axis of the MMF produced by this winding. Now in the electrical machine there are likely to be more than one machine windings, and let us look at the developed view of this. That is the way normally machine windings are represented. This is just to see how the spatial axes are then separated. Now that particular one winding is then shown here. You can see that this coil comes in, this turn comes in and then travels around, goes to slot number 7, comes back and goes here. So what we have shown in the earlier figure, in this figure, is the R phase shown only up to this point, beyond this is not shown. Now in this case what we have been seeing so far is that if we plot the MMF distribution of this stator winding, since there is going to be flow of current in this, the flow of current in this bar, let us say, is going in to this, and then this current goes along this bar. Here also you have current flowing in, and here you have current flowing out, here you have current flowing out. The nature of the MMF then, since currents are flowing in here, you have a variation, assuming that the slotting is not there and whatever is spread uniformly. This we have discussed earlier. The MMF distribution may be drawn as a straight line till this point, and then it remains constant until you reach here, and now the currents are flowing in the opposite direction, so it decreases linearly and then it remains constant over this region and so on. So now you have, this is the trapezoidal nature of the MMF which we have seen when we considered the distributed winding self inductance. It is the same thing that happens here, and if you plot the fundamental component of this, that would reach a peak right at the middle, and therefore the axis of the R phase winding is considered to be along the place where the maximum of the fundamental component occurs, and that is at this point. Now if you consider the coil that is marked in green, so you have current flowing in here, current flowing in, again current flowing in, and at these 2 points currents are flowing out, and therefore for the green phase the MMF distribution would look like this. It is again linearly varying, assuming that it is uniformly distributed, and then constant here, and then it linearly varies here, and that would have its axis situated exactly here along this line. And now you see that there is a separation between the axis of these 2 windings. These 2 windings will generate maximum MMF along 2 different directions if excited. What we are now interested in is assuming that the R phase winding is excited. We know what is the variation of MMF around the air gap. We want to find out what is the flux linkage on this green stator phase. If we find out the flux linkage, then the ratio of flux linkage to the exciting current in the R phase will give us the mutual inductance. One can also look at a picture of the machine as it would appear in 3 dimensions, so as to get an understanding of how the spatial axes are split. So, here you have, again we have seen this as an animation before. So, now you see that the R phase winding occupies one phase spread here and another phase spread somewhere here, and then the green winding occupies a phase spread here and then a phase spread here. Now, the blue winding occupies here and here. Now, if we look at the axis of the R phase winding, that would come, as we have seen in this case, right in the middle of the last coil side of the R phase, and here the first coil side of the R phase as we progress from left to right. So, that means in this diagram that would come, you have seen an R phase here which enters here, and you have the other set of R phase coil sides. So, that would come right at somewhere here. As far as the green phase is concerned, that axis would come somewhere here. Assume that you have a line connecting the center of the stator to these two dots and going out. So, those two will then represent the axis. The angle between the axis is 30 degrees, is 120 degrees. Remember that this is 120 degrees electrical. Now, if you look at this arrangement, you can see that there are 24 slots in 360 mechanical degrees, and therefore, the slot angle will be 360 degrees by 24, which is 15 degrees. So, this is 15 degrees mechanical. Being a 4-pole machine, this is also equivalent to 30 degrees electrical. And now one can see, if the slot angle is 30 degrees electrical, you now have here between the axis of the R phase and the green phase, you have 1, 2, 3 and 4 slot angles, which means that the phase displacement of the axis of these two coils is 120 degrees. That is what we have written here. This being a 4-pole machine, this is the arrangement. So, let us instead consider only a 2-pole machine to simplify our drawings. So, if it is a 2-pole machine, then what would happen is you have the stator which is there, and now in this 2-pole machine you are going to have two phases. Let us consider the R phase. Let us say the R phase is distributed here and the return conductors are placed here. The axis of the R phase winding would then be, as we have seen, in between the last conductor of one phase spread and the first conductor of the other phase spread, right in the middle of that. So, you have the axis of the R phase sitting here. Now, the the green phase axis is 120 degrees displaced away from this. So, if we are to have that, then you need to have a coil spread which has its axis along this direction, this being 120 degrees. If that is the case, then you must have the coil here. So, this figure means that you are having conductors that are uniformly spread in this region, uniformly spread here, uniformly spread and uniformly spread. Let us assume that this uniform spread is as before Z conductors per radian. We have seen all this before. Now, we are going to find the mutual inductance between these two windings, mutual inductance between the two windings, and in order to do that we are going to consider R winding to be excited and find the flux linkage with G winding. This is our approach. So, how to do that? As before, we try to draw the MMF distribution of the R phase. We know that the MMF distribution, the wave shape is known, and then we resolve that MMF distribution into Fourier series and consider only the fundamental, and we know that the fundamental of this MMF distribution will be f hat. The amplitude of the fundamental of the MMF distribution will be f hat is equal to 8 times Z by 2 pi into Is into sine of beta by 2, where beta is the phase spread. This we know. Now, what we want to do is to find out flux linkage with the G phase. If you remember how we did the derivation for self inductance, we took an elementary coil in the winding in which we want to find out the self inductance, found the flux linkage there, and then we did another integration. So, we will follow the same approach. Now, we need to consider an elementary coil, and as before we will consider this axis for alpha, that is alpha equal to 0. We will consider an elementary coil at some place here which is at an angle gamma from the alpha reference axis. So, a small angular displacement of d gamma here, and then the elementary coil at gamma having number of turns equal to Z times d gamma. So, what we have is a coil here. The return conductors of that coil will be at this point. We want to find out the flux linkage. How to find out the flux linkage? We will have to integrate over an area spanned by this coil that is located at gamma. So, in order to derive the expression for mutual inductance, we consider the flux linkage in this elementary coil at gamma, and that can be written as d psi s, which is the elementary flux linkage. That is then given by the number of turns in this elementary coil, that is Z times d gamma, multiplied by the flux that is going to pass through at any given angle alpha. This expression is similar to the ones that we have written earlier, that is f d at alpha divided by the reluctance, let us call it R d, and then f q at alpha divided by the reluctance R q. We know that RD is the length of the air gap LGD divided by mu naught RL d alpha, and RQ is LGQ divided by mu naught RL d alpha, and therefore this expression becomes Z times d gamma multiplied by Fd at alpha is nothing but f hat cos theta r multiplied by sine of alpha minus theta r divided by LGD plus f hat sin theta r multiplied by cos of alpha minus theta r divided by LGQ and multiplied by mu naught RL d alpha. So, from this is the flux linkage in the elementary coil due to the flux passing at a given angle alpha along the span of this elementary coil, and in order to get the flux linkage of this elementary coil, let us call that by the term delta psi s. That is then integral of this d psi s, the integration performed with respect to alpha as we move along the circumference of the stator, the inner circumference of the stator. In this case alpha goes from gamma minus pi to gamma, no, it is not gamma minus pi to gamma, it goes from gamma to gamma plus pi. Remember that this coil ultimately has to have an axis 120 degree displaced with respect to the first coil that we are considering. When finding out the self inductance of this coil, we had considered integrating along this area, and now when this axis has shifted we need to do the integration there, and therefore this is gamma to gamma plus pi, and that can then be done as Z times d gamma. Remember alpha is the variable of integration, not gamma at this point of time, therefore this is mu naught into r into L multiplied by f hat into cos theta r, and then integral of sin theta r is minus cos of alpha minus theta r going from gamma to gamma plus pi, and then plus sin theta r sin of alpha minus theta r divided by LGQ. This again goes from gamma to gamma plus pi. So, if we look at the first part of the term, what we get is, that is cos of gamma minus theta r plus pi minus cos of gamma minus theta r, that is equal to minus 2 times cos gamma minus theta r, and then we look at the second term, that is sin of gamma minus theta r plus pi minus sin of gamma minus theta r, that is minus 2 times sin of gamma minus theta r, and therefore this expression delta psi s can be written as 2 times f hat Z d gamma mu naught r L multiplied by cos theta r cos of gamma minus theta r divided by LGD minus sin theta r sin of gamma minus theta r divided by Lg This is the flux linkage that is caused, that arises in this elementary coil at an angle gamma, and therefore if we want to find out the flux linkage of the entire phase spread, this again has to be integrated. Now the variable of integration is gamma, and therefore psi s is nothing but integral of this delta psi s. Now the integration variable is gamma, that varies from delta minus beta by 2 to delta plus beta by 2. Note that if we go back to the figure, gamma varies from this, the angle between alpha equal to 0 axis and the midpoint, the median line of this phase spread is equal to delta, and from delta you are now looking at beta by 2 this side to beta by 2 that side, and therefore gamma varies from delta minus beta by 2 to delta plus beta by 2, and that is what we have written here, and that then becomes 2 times f hat z mu naught r L into cos theta r sin of gamma minus theta r by Lgd, this going from delta minus beta by 2 to delta plus beta by 2 minus sin theta r by Lgq into cos of gamma minus theta r, it is integral of sine, therefore that becomes plus delta minus beta by 2 to delta plus beta by 2. And again let us take a look at the first term, that is sine of delta minus theta r plus beta by 2 minus sine of delta minus theta r minus beta by 2, that is the sine a plus b minus sine a minus b form. So that is 2 times cos of delta minus theta r into sine beta by 2, and then if we look at the second term, that becomes cos of delta minus theta r plus beta by 2 minus cos of delta minus theta r minus beta by 2, that is cos a plus b minus cos a minus b form, that is minus 2 times cos of sine of delta minus theta r into sine beta by 2, and therefore this expression psi s can now be written as 2 times, we take this 2 also outside, which means this becomes 4 times f hat z mu naught r into L divided by, multiplied by cos theta r cos of delta minus theta r minus divided by Lgd minus sin theta r sin of delta minus theta r divided by Lgq multiplied by sin of beta by 2. And now let us expand this f hat. We know that f hat is equal to 8 times z sin beta by 2 into Is divided by 2 pi. So if we substitute this expression for f hat, then what you get is psi s is equal to 32 times z square sin square beta by 2 divided by 2 pi into mu naught r into L multiplied by cos of theta r cos delta minus theta r by Lgd minus sin theta r sin of delta minus theta r divided by Lgq multiplied by Is. Now when we did the derivation for the self inductance of a particular phase winding, we defined 2 inductance terms. One was LD, which was equal to 32 times z square sine square beta by 2 into mu naught R L divided by 2 pi into LGD, and we defined a term LQ which was equal to 32 times z square sine square beta by 2 into mu naught R L divided by 2 pi into LGQ. So, if we look at these definitions and our expression that we have derived now, what we can see is that psi s can be written as LD multiplied by cos theta r cos of delta minus theta r minus LQ sin theta r sin of delta minus theta r, this whole thing multiplied by Is. Remember, this expression is flux linkage in one phase by exciting another, and therefore the expression in this is nothing but the mutual inductance between the two phases, and therefore we now have an expression for mutual inductance which is the ratio of psi s by Is, which is LD cos theta r cos of delta minus theta r minus LQ into sin theta r sin of delta minus theta r, where remember delta is the separation in the axis of the two phases. We have this figure here, and this angle from here to here is what we call as delta, which is the spatial separation between the two axes. Now, if we call this as R phase and we call this as the G phase, then this is the mutual inductance between R and G, where the rotor axis is situated at an angle theta r somewhere in between. So, using this expression, delta is the spatial separation. Using this expression, we can now derive specific values for the case of a 3-phase machine where normally delta is 120 degrees in the case of 3-phase machine, and the same expression can be used to derive the mutual inductance between R phase and G phase, R phase and B phase, and G and B also, and that will then help us to write the expressions for the electrical equations for the machines. Having done this, our next task will be to write the expressions for the electrical equations and see how we can compute the behavior of the machines using that. We shall see that in the next class. We will stop here for today.